current tools like this is very computation intensive, so we need to do something to minimize time, and we need to do something to improve performance. So throughout the time, people have done different things. So they have moved into NPI implementations, GPU implementations, and etc. So next, this is the concept like we came up with after reading a couple of papers. So basically, the first understanding is like any neural network representation can be transformed into a Boolean input and output format. So if we assume that we can go with the bitwise neural networks, and in that there are some other categories like binary weighted binary input XNOR neural net. That's the thing that we are going to use today. So here in XNOR network, what happens is the input data and input vectors or input filters, everything is in the binary format. So that's the unique thing. And in our project, what we are trying to do is we are going to do the feed-forward neural network using CNN. We just do this feed-forward part, and we use the XNOR pop count to do this. So these are the objectives of our project. So first we did some literature review, we understood the background of the project, then we move on to the CNN using binary weighted CNN. Then we think about implementing XNOR using VHDL, and also pop count, bit count operation using VHDL. And also we have created an API. So our framework dynamically downloads all the images, converts it into binary format, and feed it into VHDL program. These are some papers that we refer. So this is the paper we were inspired by reading. So this is the thing we are going to implement. And also we did some other research on similar work. So I'll jump into what are the things that we are going to present you today, basically regarding our project. So this is the brief overview of the project. So we're going to start extracting images from the ImageNet dataset. Then we are going to introduce a filter. So here we can use any filter. So we use a filter of 3x3, and here first we convert this input into a bit 9-bit configuration. Then we save these files in ASCII format. Then we this is the first part for the Python pre-processing, and this other part we are going to do the XNOR pop count, and finally we are going to again use the Python API to reverse the process we did in XNOR. I'll explain this in detail. So first, what we are going to get is we are going to get a colored image. This will be a 3D matrix. Then we convert it into a grayscale. So this one is going to be a 2D matrix. Then we crop it. We do the cropping when we increase the performance, or in order to understand only the features that we need to get to the experiment. Then we convert this into a binary format because, as I explained earlier, this is binary weighted. So the input should be ones or zeros. So this is how we convert it. So I'll explain how this is done in file level. So first of all, the filter. The user inputs a filter like this. So he can give the framework the filter like this, and the framework converts this into a vector. We convert it to a vector in order to do the multiplication really fast in VHDL. I'll explain later. Next, this is the original image we extracted from the grayscale image. So it has values 255, 253, and many other values. So what we need is a 1, 0 value. And also, if you are using a filter, we need to do padding because we don't need to lose the edge information. So basically, in this step, what we are doing is we are going to first pad the image using 1. So this is being done to all the boundaries of the image. So first we do the padding. So it's in this file. In the next step, what we are going to do is we convert this into a binarized format. So all the values in this file, they are in zeros or ones. So this is binarized. But for the VHDL program, what we need is the more processed output, because in VHDL, reading files and processing the files is a little bit tricky. So that's why we use the Python API to do all this hard work. Then we make the sliding window matrix. This is done by, if we are using a 3x3 filter, we need to multiply each element in 3x3 filter with the 3x3 patch we select from the image. So we create sliding windows with respect to each part. So we'll be multiplying this vector by means of the 1/9 filter vector. So that's why this is transformed into this layer. So that's what we did for the pre-processing part. This has been completed. So basically, in our framework, there are two inputs to the hardware level. We have one filter file, and we have another file with the sliding window added image data. So nothing has been changed. What we only have done is we have added padding, and then we have added a sliding window so as to improve the performance and to make the calculation done really fast. So this part will be explained by my colleague Kadupi.
Thank you, Vibhasa. So now we will look more into the XNOR operation and how we can validate our method. So as Vibhasa explained, what we have been doing is like to convert conventional convolution into XNOR pop counting followed by scaling if we have to verify the process. So here, so in the previous slide, we had this sliding window input, which is a form of a vector which is having 9-bit pattern. So here, I'm explaining this 9-bit this can be considered as the filter, and this can be considered as the one particular vector, raw vector in that file. So if we just take this simple example from the literature review, we found that if we have to verify this, we will have to do some scaling at the end of the pop counting in order to verify it with the conventional multiply accumulate method, which is used in the convolution operation. So other than that, we will also have to convert the input vectors into bipolar form in order to make those two compare. I mean, so here you see in this particular example, we get +1 for the convolution operation and +1 for the bit counting operation, and when we do the convolution using bipolar notation, we get -3, and the scale result of the book counting is also -3. But if we take some other example, this +1 equation, I mean the pop counting just being similar to the basic convolution will not fall. So here it is not similar, but if we scale the result and then if we do the bipolar notation for the convolution operation, that means the basic multiply accumulation method, that equality will be false. So this is our VHDL approach for the XNOR pop logic. So in this circuitry we have defined two inputs for vector multiplication, vector XNOR pop operation, and this R is used to do XNOR operation and fetch into this vector, and this part is yet to be implemented. You will see that this is done through a integer addition. We are planning to convert this into a binary counter, 9-bit binary counter. So that is the part left to be implemented, and this thing scaling is done for the sake of the comparison between the Python converted, basic multiply accumulate method, and to compare the XNOR pop output for our image. And if we go to the results comparison, what we have, so we did all this with this particular pop counting mechanism. We did not implement this in binary form, circuit level yet. It is yet to be implemented, but the framework is complete. Like, so we get the binarized input image, and then we vectorize it as explained, and we have the vectorized filter, and then we do the MAC operation using a Python convolution code, and then we do the reverse windowing. And here we do the XNOR pop counting using the previous logic I have showed you, and then here we have actually compared these output vectors and one element to each element, and it was 100% similar. So which actually verifies our process. So this is one screenshot which was taken in the when the simulation going on for one particular iteration in MAC operation. So you see this is the result, output result we have taken, and we have so this is the input image we have fed into the system, and then this is the output. So we have taken the subtract to highlight what was the difference in the image. So the filter we have taken was not a Lagrangian filter, or it was also not a median filter, but we just selected some kind of filter, random filter, but what it has been doing is it has it has sharpened the image, which of course when you sharpen the image, the noise level increases. So it has been happened here. So this would be the deliverables in our project. So we will be basically providing all the data files generated and input files and output files used for this project. And the only part which is partially completed is this VHDL implementation for XNOR for counting operation. And if you go to this GitHub link, you can follow up our progress and how we had implemented this, and everything is there. So there's a documentation page as well. So in progress, we have this thing I have been mentioning this. So we have to implement that above counting using 9-bit counter maybe. So we are open for suggestions about that. These are the references. Now we are open for questions. Thank you.
I think you spend a lot of effort in preparing this presentation.
Yeah.
This is very good.
Because it was hard to deal
Yeah.
with,
Could you go back to the binarization slides? You have a slides to show how to do the binary. Yes, this slide. So I'm afraid that the actual input binarization is more complicated than this than this picture. It's just a very simple simplification. I cannot say this is wrong, but actually in the first layer they do some multiply and to binarize the input. Here it seems that you only
we have used a threshold to do the binarization.
So remember that you have the range.
Basically it's simulated as well.
Did you find the source code of XNOR net online?
VHDL?
Online? No. Maybe TensorFlow.
No, we did not.
Everything is in like plain Python.
The point here is that you don't have to process the input.
Yeah.
You can just assume that you get some input from existing software, like the TensorFlow. They have some Theano code or TensorFlow code. I don't know. I'm not sure, but you can use that existing code.
So we wanted to build the framework, so it downloads it
Okay.
from ImageNet, it processes it, and
Okay.
we feed it.
Okay.
We just wanted to build the framework.
Okay. My suggestion is to do some improvement on this part.
Okay, by the way.
And the next one is the 9-bit counter.
Yeah.
Stop. So basically, you only can count 1 per cycle.
Yeah.
I can see that you almost finish the VHDL part. My suggestion is to improve this. Try to count more bits within 1 cycle.
Okay.
For example, I give you a 64 bits string.
Okay.
Can you count the 1 among 64 bits
Yeah.
each cycle?
Yeah. So you mean basically we have to think it like here we are limited to 9-bit filter. We have to increase the filter. Yeah. So I said that we will have more bits to count in the XNOR operation.
9 is too small. 9 is too
So you mean
small.
like a filter like 8 by 8, so we have 56.
Yes.
Yeah. Okay. Yeah. We can do that.
We can do that, yeah, of course. We just have to change the register.
I mean, of course, this 9-bit counter still works. But if you want to achieve higher goal,
Yeah.
you may try the pop count engine.
Yeah.
Count 64 bits maybe within 1 cycle. Yeah, that's all.
Yeah. So I have one question. So I'm still not sure about this thing. So in the actual implementation of XNOR, so I was referring one of your papers. So in the actual implementation, we don't need this, right? I mean the scaling part.
No.
Yeah, I thought so.
Okay.
For the sake of comparison, we just
Okay. Any questions? Thank you.